My name is Hadas Hochster, and I'm a PhD student of Professor Rami Haj-Ali from Tel Aviv University in Israel. And I'm going to present about artificial neural networks for nonlinear and fractal micromechanics. This research was done in collaboration with Professor Anthony Was from University of Michigan and his team. Lieutenant Colonel Noam Shemesh from Israeli Air Force, and Dr. Vipul Ranatunga from Air. And we're talking mostly about the composites for the aerospace industry, and we are focusing on the micromechanical methods that aims to predict the effective properties of the composite lamina and their behavior. And we're researching the unit cell, the repeating unit cell. Mainly, most of the times it includes fiber matrix and sometimes the interface between them. And our micromechanical method is the PHF-GMC, and the parametric high fidelity generalized method of cells. And in our case, you can see here the RUC constructed from the lamina in double periodic material or lamina. We can use a two-dimensional RUC, and it sometimes seems like finite element analysis, but it's actually not. Between the RUC is divided into subcells, and between every two neighboring subcells, the continuity of the average displacements and tractions are enforced. And at the boundaries of the RUC, the periodicity boundary conditions are enforced. And we're using the latest formulation of the parametric high fidelity generalized method of cells based on the virtual work formulation. And next we will present the artificial neural networks. It's a machine learning model that is based on the biological neural network. It includes input layer of neurons, output layer of neurons, and hidden layers between them. And every neuron receives a weighted sum of neurons from the previous layer. And in the training process, we give the ANN the known inputs and outputs, and it learns and updates the weights by that and by minimizing the error between the outputs and the target outputs. And after the training is done, the parameters are set, and the neural network can receive new inputs and know their outputs, predict the outputs. And I'm going to show you today two NN models. One is for an ideal RUC and the PHF-GMC simulations, and one is for RUC with microcracks inside of it. And so here's the first artificial neural network. We took the RUC of IM7 977.3 carbon epoxy lamina, and the ideal one, and we did a lot of PHF-GMC simulations on that for many multi-axial applied loads, and we insert into the ANN these strains as inputs and the stresses as the outputs, under the assumption of plane stress for unidirectional lamina. And when we learned in the training process, we insert the strain classes using the theta and alpha and the magnitude in order to allow systematic training and then prediction. And here you can see the results of the NN training based compared with the PHF-GMC simulation results. You can see here the longitudinal and the transverse and the shear stress and strains for the many applied multi-axial loads. And after the training is done, we can test the network and to see what we learned, and we inserted into it patterns that were not learned in the training. And we can see here also, compared with the PHF-GMC results, the NN results for passes that were not part of the training. And that was for the NN for ideal RUC. And we are moving forward to the micropract. Here is some background. Transverse crack is one failure mechanism that by previous research in the literature initiates with interfacial bonding. And as the specimen is further loaded, the interfacial bonds merge together, and then the transverse crack grows. And the cohesive PHF-GMC model aims to predict those interfacial bonds and the transverse crack. Our model includes two sets of cohesive parameters. One is for the interfacial fiber matrix interface, and one is for the rest of the matrix. And that allows the damage to grow in an arbitrary path between the subcells. And between two PHF-GMC subcells, the discrete cohesive subcell is being implemented. 1 and 2 are the active degrees of freedom, and 3 and 4 are inactive, that store information only about the length and orientation of the subcell. And here you can see this model in action, including the interface cohesive subcells and the matrix cohesive subcells, and then the transverse crack grows. And we simplified it a bit, and we took another RUC for boron aluminum unidirectional lamina, and with initial cracks of 30 degrees in the top and the bottom of the RUC. And again, we trained the ANN based on this RUC multi-axial applied loads, again under the assumption of plane stress. We took the strains for the inputs and the stresses for the outputs. And here you can see the results of the transverse and the shear responses for the training compared to the cohesive PHF-GMC simulations. And after the training is done, the parameters are set, and we can predict. We can see the prediction of the ANN for a strain test that was not learned before. And to summarize, two ANN models were presented. One is for the ideal fiber matrix interface, and one is for the damaged RUC. And the ANN PHG models are accurate with less than 5% error in the verified predictions. And the models can be used as a standalone nonlinear behavior model, or to be extended as hybrid or surrogate model in finite elements analysis. Thank you. Thank you, everyone.
Okay, we have a good amount of time for questions. Yes, please.
Yes, thank you for our presentation. So in your simulation with the periodic RV of composite material, you showed results and predictions for uniaxial loading, right? So can your model predict the elastic behavior of composite under multi-axial stress states? So you validated that the shear or tensile compression, right?
Yeah.
But can you predict the elastic response of your RV and the multi-axial loading?
Yeah, that was for the multi-axial loading. Just from the presentations, we did it like in 3 graphs, but actually it's the same simulations, including multi-axial loads.
Right. And what is the material model that you have for the constituents?
One is for the carbon epoxy, the ideal one, and the next one, the damage was for boron aluminum.
No, but I mean the RV of composite material, we have this plastic behavior, right?
From the ghost.
So
yeah, for the matrix.
The material model we have for the matrix? It's a
Rami Osgood, the formation.
Okay, thanks.
Yeah? Okay.
Okay, yes, please.
Thank you very much for your interesting presentation. So, during the learning, you divided your data into two parts, lab training and test samples. Tell me please, how many percent have each of these samples, training and test?
80 and 20% for tests. Yeah. Thank you.
So you didn't use the data for like validation, only training and testing, no validation of the model?
Testing and validation, I think that's pretty much the same for many.
No, validation happens during the development of the models, and if you don't do, we have very high chance to overfit your model, and then we don't know.
Yeah, so we talked about what happens after the training. I mean, I don't know how do you call that?
No. When you are developing your model based on the training data set, you validate it during the development
Yes.
of the model, and that is called validation data set. And you must have 10% to 15% for that. If you don't do, your model will overlearn, and that leads to overfitting.
Yes.
So your model will be very nice during testing, but if we give new data set, it will not.
Okay, the prediction that I saw
And
after
also,
the
I feel
training
you
and
have
the
not shown the
validation.
architecture of your ANN.
You want to actually the use of many packages is now popular, but we
No, I mean, we must know what is the number of neurons in a hidden layer,
in the hidden layer 30 for each hidden layer. Yeah.
and how do you arrive at that number? So I think these are
The
very...
ANN that we developed is updating the weights during the training process with respect to the iteration number, epochs, and the
Yeah, but that does not optimize the number of neurons in the hidden layer. How do we know that, okay, this much neurons I will have in the first hidden layer?
That wasn't the first assumption of the neurons. It's the ANN updated the neuron numbers in order to get to the 30, especially here. Yeah, that depends on the optimization of the ANN. Based on its.
Yeah, ANN will optimize the weights.
So let's continue after the session. Other questions? So, yes.
Yeah,
please.
thank you for the interesting work. So I was thinking, how many data did you have for training and testing?
Over 10,000 pairs. Yeah.
Right, and how did you generate the multi-axial loading paths randomly? I think you generated randomly different loading paths, right?
It wasn't randomly. It was based on the strain pattern. We tried to project them on 3D coordinate system in order to allow this systematic training, and that allows a bit less pairs than you need if you do it arbitrary.
Okay. And the last question is, did you try other networks like RNN?
No,
Recurrent
not
neural
yet.
networks? Okay.
Not yet. Thank you.
Okay, any other question? Yes, I just have one. So that goes back to the very first question. You train the model with tensor loading and then shear loading separately. But the ultimate goal is to know the behavior under combined loading.
Yeah.
So did you do any predictions for combined tension torsion loading or tension shear loading?
Yeah, so that was, we put it on 3 graphs only to get it, to look at it, but actually it was trained based on multi-axial loads and multi-axial combinations of loads, not only longitudinal or transverse and shear, but also the combined.
So in the interest of time, I guess I have to look at the paper to get the details. Okay, thank you.
Thank you very much.